Hello and welcome to this Royal Society videocast. I'm Wendy Barnaby and today I'll be talking to Professor Cyril Hilsum, who worked for the Ministry of Defence for many years and then was Research Director for GEC. He's also Visiting Professor of Physics at University College London. He's written an article in the 350th anniversary issue of the Philosophical Transactions for the Royal Society A. And this article relates the history of flat panel electronic displays, the sort of thing we're familiar with these days from our televisions and computer screens. So, Cyril, what are the crucial technologies that make our computer and television screens the way they are now?
There are two basic points about a television set. The first thing is you've got to have some effect which impinges on the eye and converts the signal that's coming into the set into something you can see. And the way in which that is done now is using liquid crystals. Before it was done with a cathode ray tube, the old kind of television set, which of course was much bigger, more cumbersome, and quite important, worked off very high voltage. The liquid crystal set uses a low voltage, which fits in much better with silicon chips that everybody knows about today. The other thing you've got to have on any complex picture forming device, like a television set, and that is pretty complex, because in fact you will have several million picture elements. You've obviously got several colors, but you've got to have depths of shade as well. So you've got to have a lot of elements, and that means that you've got to have some way of putting information on each one of those picture elements. Now, the way in which that is done in modern sets is to have a little switch at each point, so you can switch the point on and off. And that means you've got to have some kind of electronic device. A transistor's a good one that you can use, and you've got to have a way of putting them down on a piece of glass, which is not straightforward, because some of the television sets that you have today are several feet in diameter. So that means you're going to have a lot of transistors deposited on the surface. And the two things, the liquid crystal and the switch, both were developed in the UK.
Let's go back to 1967 then, when electronics was really in a revolution. People were trying to make things smaller, using less voltage. And the Minister of Technology, John Stonehouse, gave a big boost to flat panel electronic displays in this country. Can you tell me how that happened?
It's a story that's not very well known. People were interested in simplifying the television set for a number of reasons. And a lot of work was being done in the States. And some people had thought of liquid crystals, but there were a lot of different ways in which you might do it. And we were interested in simplifying displays because through the Ministry of Defence, we were developing very small radar sets. Now, we'd moved from the radar set that worked off very high voltages for the vacuum tubes that gave us the radar radiation to tiny little radar sets. They were about 10 centimeters cube. And then it seemed silly that to show what the radar set was doing, we now had to go to a cathode ray tube display, which was far bigger than the radar set. And we thought, isn't there another way? But while we were thinking about that, our task was changed because we were moved from effectively defense research into the Department of Technology. That was at the time that the Labour Party had just taken over and were going to make sure that the country was developing science, and it was called the White-Hot Technological Revolution. And then John Stonehouse came down to our establishment, and for some reason, the director of the establishment, a very nice mathematician called George McFarlane, he said to Stonehouse, people don't seem to realize that we spend a great deal of money on licensing inventions from the United States. And Stonehouse said, well, give me an example. And he said, well, for example, the color television tube that is now coming into our homes, remember it was a long time ago, it wasn't that normal, but people were beginning to adopt them. He said, that tube is costing us more in licensing fees than we're spending on Concorde. Stonehouse phoned George the next day and said, "Director, you have convinced me." And George said, "Well, good, Minister, good." "Exactly what about, Minister?" And he said, "About the need for a flat panel display program." And George said, "Oh, yes, Minister." He said, "So start one." Well, George then summoned me and my boss, who was head of physics, to his office and said, "Can we make flat panel displays?" And I said, "No." He said, "Oh, that's not very helpful." I said, "It's true." So we had a working party which studied the problem, and it went on for about a year or so, and at the end, after some hiccups, we came up with a recommendation that we should work on liquid crystals. We had some other things we were going to work on, and we realized very early on that the key to liquid crystals catching on was to make something that lived.
So if you talk about liquid crystals that live, what do you mean by that?
They keep their original properties for many years. Now, it was fortunate that I had discovered a very bright organic chemist at Hull University who was getting quite depressed because his work wasn't being recognized, but he impressed me. And we decided to give him a contract. And we placed a contract with George Gray. He's now Professor George Gray and holds the Wolf Award, which is second to the Nobel Prize, Japan Prize. And we gave him a contract of £2,000 a year. And within a year, he'd come up with a stable liquid crystal. Quite original, nobody else had it. And this was the foundation of liquid crystal television, basically, and all liquid crystal displays. For many years, the material that originated at Hull University, which was improved by a young scientist, a PhD graduate, who was at Malvern with me in my group, he showed how you could make it more practical, because it isn't just one material. Any liquid crystal used in devices employs about 4 or 5 different materials, and that mixture has to be tailored to give you the right temperature range and the right performance. And Peter Rain showed how that could be done. So the two groups working together came up with this material that in the first place meant that people could make watches and scientific instruments, and later on led to displays for television. And then we had to have the problem of how did we convert this into a complicated picture.
And this is where the switching comes in.
This is where the switching comes in. It's called addressing because essentially you give each little bit of information a place it is to go to on the screen. And that effectively is an address. It's going to be some centimeters away from the left-hand edge and some centimeters away from the top. And that is going to progress all the way down. So each little point on your television has an address. And you have to find a way of ensuring that when you put information onto your television set, it goes to that address and to nowhere else. And that is a real problem because it can hunt around if you're not careful and finish up in places where you didn't imagine it could ever get. And that confuses the observer because they don't get a clear picture. But if you have these little transistors everywhere, then that sorts the information out. And that was fine in principle, but we couldn't find a transistor or a switch that lived. We could get the devices all right, but they would change with time. Well, the one thing that people did know, and this was the difference between the new electronics and the old electronics, was that silicon did last. Silicon devices had been made to last. The old vacuum tubes that they replaced lasted for a few thousand hours, and it was fairly normal to have to change a vacuum tube in your television set or in your radio set. But once transistors came in and once chips came in, one of the great advantages was they lived for a long, long time. And all of the switches that people had come up with that they recommended to us and that we worked on were made of materials like cadmium sulfide, cadmium selenide, exotic materials that performed but didn't keep performing. But once we thought we could make something in silicon, this everybody would agree was going to live. Unfortunately, there wasn't an easy way of taking your crystalline silicon from your chips and putting it on a panel that was several feet in size. You would have to stack them all on and stick them on. What you wanted was something you could deposit. And then the group in Dundee University came up with another form of silicon that you could deposit on glass and cover large areas. And this seemed a great way forward. And on Christmas Eve, I think it was 1978, a small parcel arrived at my lab, and very excitedly, I turned on a liquid crystal using them. And that was the beginning. And those are the devices that you now have in your television sets. They started at Dundee University. We developed them, improved them, of course, and they're still there. There are different forms now that people are using, but that's the basis of, I would say, 3/4 of the television sets that you now have.
Now, this is fascinating because that means that by, say, the end of the 70s, early 80s, 30 years ago, all this basic science was in place. And since then, what's happened, so that we see the screens we have today, have been improvements in the manufacture of liquid crystals, the better angle of vision, the contrast, and so on.
It's called engineering. You can say this, a lot of the science was done then, but of course it wouldn't have given you a flat panel television if it hadn't been for engineering.
Well, these developments are pretty exciting, aren't they? I mean, do you think that we'll go on to see 3D television?
That almost certainly will happen. Of course, it is with us when you're using glasses. Those glasses essentially work very well with liquid crystal screens and with pictures, and you can have a pair of liquid crystal goggles. It is relatively easy to make a 3D picture for one observer, because what you do is you send a different picture to the two eyes. Now, what they have done is they have also coupled that with detecting where you are, so that when you move your head, the 3D effect goes with you. The problem then is having your family watching, because the system will get confused as to whose movement it is coping with. So that isn't yet solved, though people are still working on it. And I did see in a large store a Samsung 3D television, quite big. It was not bad. It wasn't for sale. It was an experiment, and they were showing it, and it wasn't bad. It was slightly blurred. It wasn't sharp enough. And Sony also, Sharp also have come up with a 3D. But there's a lot of money at stake here, so I expect it will happen.
Well, thank you, Cyril, very much indeed.
Thank you, Wendy.
And the title of your article is Flat Panel Electronic Displays, a Triumph of Physics, Chemistry and Engineering. And that's all from this 350th anniversary Royal Society podcast. We hope you've enjoyed it.